Alright, that's good enough. Okay. So where we ended last time was a brief discussion of limits, if you remember. And we skipped over Theorem 11.7 because the class just seemed kind of done. So we'll be picking back up on this theorem on page 198 real quick, and then we'll go back to talking about limits. So Theorem 11.7 is the perimeters of regular polygons with the same number of sides are proportional to their radii or their apothems. That's what we're going to prove. In short, if I have two regular polygons, one with perimeter P and the other one with perimeter P prime, that's going to be equal to, or proportional to their radiuses, which is going to be proportional to their apothems, is what that's saying. So I'm trying to prove that this ratio equals this ratio equals this ratio.
Are apothems radii?
Or
are they different?
So what it is if I have some regular polygon inscribed in a circle, so some circle and some regular polygon inscribed in it, and then if I take the circle that is inscribed inside that regular polygon, it's going to be tangent to each of these sides. Were you here last class?
Mm-hmm.
And yeah, it took me a second to get the lecture up. So yeah, we can recover that terminology real quick. So there's a center of both the circle inscribed inside the regular polygon and circumscribing the regular polygon. Doesn't matter how many sides this thing has. I drew a hexagon. But that doesn't matter. So what we proved is that any regular polygon can be both circumscribed inside a circle, meaning all its vertices line up on one circle. So it's possible for me to construct a circle that contains all its vertices. And then I can also have an inscribed circle, which is one that is tangent to all its edges. So it is possible to construct both those circles. We call the center of both those circles are centered at the same point. We call the center of both those circles the center of the regular polygon. We call the distance from here to one of these vertices, to the outside circle, the radius. And we call the distance from here to one of these points of tangency on the inside circle, the radius of the inside circle, the apothem. So the radius, the apothem, and then the perimeter is the sum of the lengths of the sides.
Okay.
Good? Okay. So going back, let's go over a big idea. So I have two regular polygons with the same number of sides. The big idea here is I want to show that, how's the best way to say this? Maybe we don't need to write out full proof since it's just you two. But if I can show that we basically know right out the door that both these triangles are similar triangles. We know that this is a right angle, this is a right angle, and we know that this angle is congruent to this angle, and we know that this angle is congruent to this angle. We knew that from our previous theorems talking about these things, showing that the central angles are the same, and that's a bisector of both the central angles, that's a bisector of a central angle, and then that bisects that angle, that bisects that angle. We already know that these are similar, so that angle is congruent to that angle. So anyways, we know that this triangle and this triangle are similar triangles. Now, what does it mean for triangles to be similar? It means that their angles are congruent and that their sides are proportional. So since these two triangles are similar, I instantly know that A over A prime is equal to R over R prime is equal to AC
length over AC
over A prime C prime. Right? Now when you have a ratio of two numbers, if I have 1/2, for example, I can multiply the top and the bottom by the same thing. It doesn't change my ratio. 1/2 is equal to A over 2A, for example. So I can multiply top and bottom of this thing, and my proportionality is still true. These ratios are still equal to each other. So I need to go from AC to the whole perimeter of this thing. Now notice AC is half of this distance, right? And this is an n-sided polygon.
Okay.
So I have n sides, or n of these distances, or 2n of these distances. So if I multiply this top and bottom by 2n, then the ratio is still true, right? And then 2NAC is the perimeter of this thing, and 2NA prime C prime is the perimeter of this thing.
And we know we can do that because they're regular polygons.
So we knew that angles were going to be congruent because of regular polygons.
Right, but we also know that all the sides are the same.
Well, we didn't even need that. Oh, it has the same, both of them have n sides. They have the same number of sides, but we didn't use the fact that this side is proportional to this side.
I know, we use the fact that all of 6 of those sides are the same.
Oh, are the same long. Yes, because of regular polygons. Is that what you're saying?
Yeah.
Yes. So do you understand the idea of the proof? Do we need to write it out? You think you got it?
Yeah.
Think it makes sense? Okay. So that was theorem 11-7. And then now we'll move on to limits. Now, in this class, when we talk about limits, we're just talking about the limit of a converging series. I don't know, have you ever come across that?
Limit of a converging series.
Yeah, so if a series converges, then we call that the limit of the series as n goes to infinity, basically. So, in short, you're probably already familiar with this, but a quick example would be, what's the limit as n goes to infinity of the series 2n over n?
Just infinity? Or is it undefined? Because it's divided by infinity.
Okay, first off, maybe make sure you understand what this is shorthand for, this series notation. That's shorthand for when we plug in 1, so 2 times 1 over 1, yeah. And then,
Oh, okay, so it's just 2.
perfect. And then it continues, da da da. So in that case, it's always 2, it's not changing.
Right.
Now, if I would have said 2 over n,
Then that would have been like undefined, or because you can't divide by.
well, what's the first
You can
term?
divide by 0, but you can divide by a very large number.
Okay, so maybe you're not comfortable with what this is saying. Oops, that's supposed to be a curly brace. So let's go back to talking about that. You know what the natural numbers are, right? So in this class, the natural numbers, they start with,
In this class,
yeah,
just
different authors do different ways. Some start the natural numbers with 0, some start with 1. In this class, we start with 1. 1, 2, 3, dot, dot, dot.
okay.
And that's the natural numbers, right?
Mm-hmm.
So this, when I use notation like this, 1 over n, this is shorthand for a special type of function, we call it a series,
Okay.
where its domain is the natural numbers.
Oh.
And its output is 1 over n. So it's the same thing as saying f of n equals 1 over n, but I can only plug in the domain. And then we use this to keep track of the order of these terms. So whatever 1 goes to is the first term, whatever 2 goes to is the second term, whatever 3 goes to is the third term, etc. So when I write 1 over n like this, it's shorthand for the series 1 over 1, 1 over 2, 1 over 3, 1 over 4, dot, dot, dot.
Okay.
Does that make sense?
Yep. So as 2 is divided by this huge, 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 huge number.
Right.
I'm saying, what is the limit of that?
Another way of saying that is, if I continue this indefinitely, what is the one number I'm always getting closer to? In other words, is there I'll say it, 0 is a number that's always getting closer to. No matter how small of a number you pick, or no matter what other number you pick, this series will eventually get closer to 0 than any other number you pick.
Right.
Doesn't matter how small of a number you pick. So it's the limit that this thing approaches. So this, the limit as n goes to infinity of this is 0. Let's look at another one real quick. The limit as n goes to infinity of, we'll do n over n plus 5. What's that?
I want to say just 1, but that plus 5.
It is just 1.
Okay.
You're thinking, oh, there's a plus 5 down here. You know how to do that real easy. But there's a plus 5 down here. But when you're talking about plugging in massive numbers with digits so long we can't even write them on this board, adding 5 makes no difference.
It's like
It's an irrelevant term.
Okay.
Let's look at one more. The limit as n goes to infinity of 100n over n squared plus 1. And let's add another 1,000 up here. Why not?
Well, since the bottom number is larger, would it still be 0?
It's still 0 because this is a higher power term. Alright, so I think you got a good feel for how these are going.
Okay.
Some quick properties about limits that you both probably already know. We're not going to prove them. There's something you've proven in calculus class. But in short, if I know that the limit as n goes to infinity of some series x of n is equal to big X, and I know that the limit as n goes to infinity of some series y sub n is equal to big Y. You okay with that notation for just some variable sequence with this as its limit?
Yeah.
Okay. Then we have some basic rules. You can go back and forth between these. I'm not sure which way they're going to write it. But the limit of the sum of the series is equal to the sum of the limits. The limit, and that's the same thing for the difference. And maybe we'll do plus or minus, plus or minus. And then the limit of the product of the series is equal to the product of the limits. And then finally, the limit as n goes to infinity of the quotient of limits where y is not equal to 0 is equal to x over y. Let's see one of these in action to get some intuition for it. We'll just pick this one. So I know that the limit of the series 2n over n is 2. And I know that the limit of the series, 5n squared over n squared plus 1 is 5. So the limit as n goes to infinity of this is equal to 2. The limit as n goes to infinity of this is equal to 5. If I take the product of these two things and take its limit, the limit as n goes to infinity of the product of these two things, that's what this is saying, of the product of these two things gives me 10n cubed over n cubed plus n. And the limit of that as n goes to infinity is 10, which is the product of those. Right? So that's a quick example showing one of these properties in action. These are kind of intuitive properties. And those are some common properties of limits. Oh shoot, we skipped 2 theorems. I didn't notice them.
From 7.
On page 199. We'll come back to them in a second when I finish talking about limits. So let's see, Theorem 11-10 is this. So here's the exact verbiage of it. Consider two sequences with the nth term xn and the y with the, consider two sequences with the nth terms xn and yn respectively, and suppose that the limit of x sub n is capital X and the limit of y sub n is capital Y. Then the sequence whose nth term is x sub n times y sub n is equal to x times y. And then theorem 1111 is this one. And I guess I didn't state this one, but this is also one. Maybe they did somewhere. So those are all our theorems with limits. He just states them as theorems. He doesn't prove them because the proofs of them are calculus. So those are our limit theorems, and we'll use those for some of our theorems. But let me go back to page 199, and let's do those two, 11-8 and 11-9 real quick. Can you see the screen marker okay?
Yeah.
Let's see if any of these markers are good. Is that better? Is it 6s?
Yeah.
Is it all 6s? Doesn't matter?
The red is pretty faint, but
Outside the red, we're good? Okay. Try the brown. One of you just want to read me theorem 11-8?
11, 8.
199.
Yeah, page 199.
Okay, so the area of a regular polygon
Of a regular polygon
is equal to 1/2 the product of the, do you see that apothem
Uh-huh.
and the perimeter.
Uh-huh. That's it? Okay.
And semicolon area equals 1/2 A times P.
Okay, yeah. So if we let A be the apothem of some regular polygon and P be its perimeter, then the area of a regular polygon is 1/2 AP. So let's prove this real quick. So if I have some regular polygon, we'll just do that. And remember, the apothem is the distance from here to here. Here's A. Then we can think about this as all these triangles. This triangle is going to be congruent to this triangle is going to be congruent. Maybe I'll just draw dotted lines problem. All these triangles are going to be congruent, right? By side, side, side. We know that this is congruent to this, is congruent to this. Sorry. This is congruent to this, is congruent to this, is congruent to this, is congruent to this. And then all these side legs are obviously congruent because of the radius of it. So the area of one of these triangles is 1/2 A times 1/n
Of P.
of the perimeter times P over N. 1/n of the perimeter. Right?
Okay.
And then we have N of those triangles. Let me erase that A. A is just the height of the triangle, right? So let's start with this. Are you good with this as the base of this triangle? The distance from here to here is the perimeter of the whole thing divided by how many sides there are. So this is the base. And then the height is the apothem. It's the distance from here to here. This is the height of the triangle, the apothem. So the formula for the area of the triangle is 1/2 the height times the base. Right? And we want the area of the entire polygon. So to get that, we have n of these triangles, which is equal to 1/2 AP. Good?
Yep.
Okay, let's see the next theorem.
Want to read that one, Mark?
My voice is crap right now.
Okay, 11-9, the areas of two regular polygons with the same number of sides are proportional to the squares of their radii. And it just has in parentheses, or the squares of their apophthegms, or the squares of their sides.
Or the squares of their apophthegms, or the squares of their sides. Because we already showed that the apophthegm is proportional to the radius, is proportional to the side, while the perimeter is proportional to the side. Right? So obviously those squares are going to be true. If I know that A over A prime equals R over R prime equals P over P prime, then obviously that's true for the squares as well. Right? So once we can show it's proportional to one of these things, we get it's proportional to all of them. And we'll probably want a picture to help talk about this. I feel like that brown is dying fast. So there's one of them, and we'll do a smaller one, I guess. Something like that. And then let's label some points. O, O prime, A, B, A prime, B prime. Okay. So, well, maybe we don't need to write all that. We already know what the areas of them are, right? Maybe the right way to work, I'll show proportional to the radius is just, why not? So I already know that R over R prime is equal to, what did we show last time? We put a C here and the C prime here. So I already know that R over R prime, R is this distance, R prime is this distance. Right? I know that R over R prime is equal to, I'll just do AB over A prime B prime, right? And I also know that R over R prime is equal to A over A prime. Good? So multiply both sides of this by this. So I get R squared over R prime, maybe put parentheses around that, squared, is equal to A times AB over A times A prime B prime. Oops, that's an A prime. You see that? Since this is equal to this, I'm multiplying both sides of this by the same thing. But over here, I'm calling it this. Over here, I'm calling it this. But those two are equal. So you good with that? And then once again, if I multiply top and bottom of a ratio by the same thing, I don't change the ratio. So I can multiply top and bottom of this by 1/2 n. So 1/2 n times A times AB over 1/2 n times A prime times A prime B prime. And notice that is the area. I could have rewritten this, n times AB is the perimeter, n times A prime B prime is the perimeter. So that's the area. So the area is proportional to the square of the radius is. And I can plug in whichever one of those I want. Does that make sense?
Yeah.
Okay. Alright, so that covers those two theorems. Now, then next would have come to limits, but we already covered that. So now moving forward to using them in whichever one uses them next. I'm guessing we're going to have a definition. Oh no, next we need to talk about the circumference of a circle using limits. So, the circumference of a circle has a pretty natural definition. If I think about the circle inscribing some regular polygon. We'll start out with the square. That's terrible. Okay, the square is going to look awful, but it's a square inscribed by the circle. And it lands right on the circle, as you can see. So, how's a good way I can say this? So, let's imagine that we're talking about let's imagine we have the sequence of the perimeters of regular polygons starting with a square. I don't know if they start with a square, but we can use the same argument. So I'm going to say P4 is the perimeter of the four-sided regular polygon, and that's what I'm going to start with. You good? And then for each one of these, I can go and plug in a point, plug in a point, plug in a point, plug in a point, and make a new one. Make a new one, and now it's 8-sided. You see that? And now I made an octagon. So I picked the midpoint here, the midpoint here, the midpoint here, the midpoint here, and now I constructed an octagon. And notice the octagon is going to have a bigger perimeter than the square. How do we know that? Triangle inequality. The shortest distance from this point to this point is that line. So going along the two edges of a triangle is going to be longer. Right? Same argument here, same argument here, same argument here. So that would be P of 8. And then I could do the same thing, adding more points, adding more points. And what does that give me? P of 16. And I can get P of 32. And I can keep on making this sequence forever and ever and take the limit of it. And I'm saying that the limit of this thing, as n goes to infinity, is what I'm going to call the circumference of that circle. Now, how do we know that this thing has a limit? I don't know if we discussed this last time or not. First off, notice that we're always getting a bigger and bigger number. That's one sign that you have a limit. You need to have your series either always increasing and bounded from above, or always decreasing and bounded from below, or just a constant. That's 3 guarantees that the sequence that you're talking about has a limit. So if it's always increasing and it's bounded from above, you're guaranteed it has a limit. If it's always decreasing and it's bounded from below, you're guaranteed it has a limit. And then if it's always constant, it has a limit. Right? Mm-hmm. So this is always increasing, which is a good sign that it has a limit. There's one more thing that we needed to show real quick, and that's that it has an overbound. And notice that if we take just the square inscribing this thing, then that's going to be an overbound.
Okay. So that's how you know it has a limit. You're not saying what the limit is, you're just saying...
We're defining the limit to be the circumference of the circle, right. But I should have first argued that a limit exists for this series. Right. Maybe the author puts that a little bit better, I don't know. Let's read his definition now. Oh, maybe he doesn't give the definition yet. Let's see. For a given circle, let Pn be the perimeter of a regular polygon of n sides inscribed in the circle. The numbers Pn with n equal to 3, 4, 5 form a sequence that has a limit. So that was a theorem he's going to prove. We did this sequence. He's probably going to switch to that instead. Let's just keep going. Remarks. The proof of this theorem involves 2 steps. First, it is to show that the sequence is increasing. That is, each term is less than the one that follows it. So this is less than this, is less than this, is less than this. Then it is shown that the sequence is bounded. That is, the terms do not become infinitely large. It then follows as a fundamental property of the real numbers that such a sequence has a limit. It is natural to ask how we know that the regular polygon with n sides exists for all positive integers n greater than or equal to 3. We do know that there are regular polygons with the number of sides equal to 4, 8, 16, etc., which is what I did here. and we know how to construct those. Therefore, the perimeters of these special regular polygons form a sequence, P4, P8, P16, P32. And by theorem 11.12 and the definition of a limit, this sequence has a limit. Theorem 11.12.
Isn't that the one he's in?
Yeah.
Unless it's already proved.
What?
I thought he was still proving it.
Yeah, so did I.
No, I guess he's done at the top of the page there. Then it follows the sequence has a limit.
I guess he's just counting on the fact that it's obvious that that thing is bounded, and it's obvious that that thing is always increasing. And he's just relying on that. Okay, so now we can give the definition of circumference. The circumference C of a circle is the limit of the sequence of perimeters Pn of a regular inscribed polygon. So the way that he finally has that written is C equals the limit of P, and he doesn't bother saying n goes to infinity. The limit P sub n is equal to C. That's our definition for it. Okay. Okay, so let's move on to the next theorem. Theorem 11.13. The circumference of two circles are proportional to their radii or to their diameters. You want to just read that to me again here in a sec? What number was it?
11:13.
Alright.
So that's page 202.
Yeah, still, it's not very good. All these markers. Theorem 11.13? Okay, what does it say?
The circumferences of two circles
Is that right?
Yeah.
The circumferences of...
Oh, you missed your U. There we go.
Thank you. So the circumferences of two circles
are proportional to their radii. In parentheses, or their diameters, period. That is, so you
Yeah.
parentheses.
If it's proportional to the radii, then obviously multiply that top and bottom by 10 and get diameter.
Right.
So, let's show that real quick. Now, we already showed...
Well, it's not quite finished.
Oh, what else does it say?
It's just saying what proportional
Well, I guess it is pretty much.
kind of
Okay.
works.
Okay, so we already know that from, what theorem was it? One not too long ago, maybe you can find it, but we already found out that Pn over P prime n is equal to R over R prime.
For a regular polygon.
For regular polygons, right? So, then, the limit as n goes to infinity of Pn over P prime n is going to equal the limit as n goes to infinity of R over R prime. Now, this is just a constant. So the limit of a constant is just a constant. This doesn't change with n. The radius is always the same. But this does change with n. And the limit of the quotient is just the quotient of the limits. So we'll skip that step and we can go straight to the circumference over circumference prime is equal to R over R prime is obviously equal to the diameter over the diameter prime. Right? And kind of ignoring this middle one, let me rewrite these two proportions because there's an important note there. C over C prime equal to D over D prime. We can rewrite that as C over D is equal to C prime over D prime. So for any given circle, the ratio of its circumference to its diameter is the same. And we have a special name for that ratio. We call it pi.
Ice cream cake.
Kind of jumping the gun there, I guess. I'm sure that he gets to it.
Next page.
So that was theorem what?
13.
1113. Okay. Theorem 1114. If C is the circumference of a circle and D is the diameter,
Oh,
the ratio.
You went through this.
Oh, that's what we just. So the next theorem is saying this. This is just rewriting this. That's a theorem. That should just be a corollary.
Yeah, corollary.
The theorem is really
equals
just a
pi
corollary.
d.
Never mind. Okay. Definition 11.8, C over D, which is the same for all circles, will be denoted by pi. Okay, and we also said that. And then, one more thing worth noting. So if circumference over diameter is always equal to pi, then we have a way to calculate circumference when we know diameter, and vice versa diameter when we know circumference. So we can say circumference equals diameter times pi, or if we knew the radius instead, circumference equals 2 radiuses times pi, or 2 pi r is the order it's typically written in. Right? That just all follows from this, same thing.
Wow, beautiful.
Yeah, this is where I started my trig class. Until I found out the book doesn't do that. Because the first day I taught, I didn't know I was teaching.
Oh, and he'll
So I
probably
just
get
had
to
to come
that.
up with something. Huh?
You're probably telling your class. Oh, and he'll get to that. On
He'll?
the next page. The author.
Oh, no, I started going through the book I used and I hate it. I'm never teaching that book again. I don't ever want to teach the class again because I don't have another book to use.
Look at that physics book.
I'm not seeing it.
Where?
Oh, the big blue one.
Blue.
Physics 1 and 2.
Nice.
Okay, so that was the definition. 11.8 is the definition of pi. Don't really want to spend too much time on the computation of pi, but there's ways that we can get estimates for what pi is. How do we get estimates for what pi is? So if we have the circle here, the way that we get estimates is we construct some regular polygon around it, and we calculate its perimeter, and then we take some regular polygon inscribed in it, and we calculate its perimeter, and then we know that the circumference is squished between those two values, and therefore you can find out numeric approximations for pi. It's nothing really impressive, but so they quickly show on page 204 how to figure out that pi is greater than 3 and less than 4 square roots of 3 over 2. Or in other words, less than 2 square roots of 3. And they just inscribe it inside a hexagon, and then they have a hexagon inscribing the circle as well, where the circle has a radius of 1. And then when you get to calculus, you'll find other ways of calculating pi to however many decimal places you want. But the numeric value isn't very interesting to me. So moving on. Area of a circle. So now let's figure out what the area of a circle is. And you can pretty much guess how we're going to get the area of a circle. It's going to be the same idea. We're going to inscribe a polygon inside of there. We'll start with a square, and then we'll sit there and increase the number of sides, taking up more and more of the area. We'll take the limit of the area of that, and whatever that approaches is going to be what we call the area of the circle. Before we do the area of a circle, maybe do a little lemma real quick. I don't know if the author does it, but it's worth showing real quick. And that is what the limit of the apothem is as we increase the number of sides. So remember, if we have a circle, that is terrible. If we have some circle, we'll do a big one and talk about it. Here's O, and we have some regular polygon inscribed inside of it. I'm just going to draw one of its sides, that's all we need. A, B. This distance from here to and here, this is R. This is one of the sides of the regular polygon. And then this right here is the apothem. Now, maybe let's calculate the apothem real quick in terms of r and this distance, AB. Well, we're going to want to use a rectangle. We'll just call this point right here B. I guess I could be C. So let's see what A is in terms of this distance and in terms of R. We'll draw it over here. And what does A equal?
R squared, square root of R squared minus AB squared.
Right. Using the Pythagorean theorem, this distance squared plus this distance squared equals this distance squared. Or in other words, this distance equals the square root of this squared minus this squared. Now, so A equals that. We want to know what is the limit of this as n goes to infinity, as in our number of sides goes to infinity, of the square root of r squared minus AB squared.
It'd have to become R, wouldn't it?
Yeah, it's going to be r. This AB, as we take more and more sides, keeps getting smaller and smaller and smaller and smaller and smaller. Right? So we know it has a lower bound of 0. And we know it's always decreasing. So it does have a limit, and the limit is going to be 0. Right? So that thing gets closer and closer to 0. So A gets closer and closer to R. That's the thing we want to know. So now let's talk about the area of a circle. The area of the circle, I'll call it A, is equal to the limit as n goes to infinity of the area of the n-sided polygon. You good with that? And we know what the area of an n-sided polygon is, limit as n goes to infinity. That was 1/2 A times the perimeter of the n-sided polygon, right? 1/2 the apothem times the perimeter. Good? Now, remember, the limit of a product is a product of the limits. So we can split this up into 3 different limits, right? What's the limit of 1/2 as n goes to infinity?
Constant.
1/2. What's the limit of A as n goes to infinity?
R.
R. Remember, A is a variable. It's the apothem. So that's R. And then what's the limit of the perimeter as n goes to infinity?
C.
C. Perfect. And if we want to write C in terms of R and pi like we're used to seeing, then this is 1/2 R times R pi. Or 2R pi, sorry. Right? Which is pi r squared as we expect. That's the area of a circle, pi r squared. It is cool. Does that make sense? And I'm sure he did something similar to that. Oops, I guess he uses SM for the area. Sorry about that.
SM.
Yeah. Oh, 1115 is just saying that the limit of that area exists. Which we already know that the limit of the area exists. Because we can calculate the limit. So I don't know why he needs to prove that. Because we already proved that. Oh, he probably didn't take the time to argue that the limit of this thing exists. So that's probably why he needs to argue that the limit of the area exists.
Well, then why did we argue that?
Because that's the way I saw it in my head.
He doesn't even mention the apothem.
Well, he has to because he's going to have to get that to R somehow. But he might have that as an argument in terms of area.
Yeah, I don't see it.
I don't know. But if he can take the limit exists.
I mean, that's...
It's a valid way to check, does the limit exist? If he can take its limit, then the limit exists. You don't need to have some argument that it exists and then find the limit. Oh, but he doesn't want to prove, okay. Yeah, it makes sense the way he did it, because then he wants a definition for what the area is, and then he wants to argue the formula for the area.
Okay.
So in Theorem 1116 is where he has this argument.
The area S of the circle is the limit of the areas inscribed by.
Let AN be the apothem of an inscribed regular polygon of n sides in a circle of radius r, then the limit of AN equals r. Right? Oh, I guess I probably should have put that subscript on here, because this is changing with each one. I should have put AN there. That's probably
Okay.
why that was confusing and why you wanted to keep that as a constant. Okay. So, Theorem 1117. The area of a circle is equal to 1/2 the circumference times the radius. Which is what we got. 1/2 the circumference times the radius. Corollary, the area of a circle is equal to pi r squared, which we also showed. Okay, so that is it for areas. So next thing we're moving on to is talking about measures of angles. And so now we're finally going to start assigning degrees to angles or radians to angles and talking about them. But we need to develop a system to do that. So before we can do that, we need to start with our arcs. So looking at definition 12.1, definition 12.1, if angle AOB is a central angle of a circle, a central angle means that the vertices at the center and A and B are points on the circle. Different points on the circle. It can't be the same point. So if angle AOB is a central angle of a circle, the arc, which we represent like this, the arc AB of the circle subtended by the angle, subtended by the angle is defined is defined to be, let's see, it's going to be the set of points on, or, let's see, it's going to be a set of points on the circle on or interior to the angle So that's one way we can have it. Let me explain what we're saying there, then I'll continue. So if I have some circle centered at O, and we have some central angle AB, then the arc AB refers to either all the points on the circle interior to this angle, so that's all these points, and on the angle, which includes these two vertices. So when we do use that notation for the arc AB, we're either referring to the set of all these points, or, if you read how the definition continues, or it's referring to the set of all these points, exterior to the angle or on the angle. When we use the outside one, we typically pick another point on the outside C, and we talk about the arc ACB, because just AB would be ambiguous. So when we're just talking about the interior one, it's typical to reference it like this. When we want to talk about this bigger one that goes around, then it's typical to do A, C, B, like that to reference
That
it.
was to the camera, let them know I came.
Leah, you're over an hour late.
Yeah, I was tending.
Who were you tending for?
Winnie.
Do I need to give her a call?
That was my job.
Do I need to pay you to be here? How much is she paying you an hour?
A lot.
A lot?
For one kid, yeah.
What's that?
I don't know.
450.
You don't know what she's paying you? So if there were
I just-
$10 sitting here for you, if you got here on time, would you be here?
No, because that's my job.
$20.
I'm not gonna let Winnie down because.
$50. $100.
I'm here.
An hour late. What would it cost me to get you here on time?
I don't know.
Jeez, you're hard to brag.
I would do it for $100.
You missed the end of our conversation of area. Let's see.
I can just go back and watch it.
Yeah, you can go back and watch it. I don't think we're gonna have to reference it going forward. And you probably memorized some of the stuff we proved, like that the area of a circle is pi r squared.
I memorized 1/2 pi c.
1/2 pi c.
Or what was it? 1/2 RC.
It was 1/2 rc.
Kids these days.
Yeah. Going straight to the corollary. Alright. Maybe finish reading the definition. I don't want to finish writing it. I think you understand it. So maybe just read it one more time looking at the picture. If angle AOB is a central angle of a circle, angle AOB is a central angle of a circle, meaning it includes its vertex is at the center, and then those are 2 points on the circle. Is a central angle of a circle. The arc AB, which we write like this, of the circle subtended by the angle AOB is defined to be the set of points on the circle that are interior to the angle. So that's all these points. On the circle and interior to the angle. Right?
Mm-hmm.
So that arc AB is the set of points on the circle subtended by the angle. Sorry, I jumped a line. Is defined to be the set of points on the circle which are interior to the angle or on the angle itself. So we include the points A and B. So A and B and all the points on the circle in between A and B. The set of points of the circle which are exterior to the angle is also called an arc of the circle. So we could talk about arc of the circle as all the points in between A and B, including A and B, or we can talk about all the points exterior to this angle and including A and B. And then as a general rule, when we're talking about the arc, that's the bigger one, then we pick some other random point, give it a name, and we reference it like this. So when I say arc ACB, that typically means this one. Well, that always means this one. And then when I say arc AB, that typically means this one. But if it's ambiguous, then you need to stick another point to make so it's not ambiguous. Okay, so that's what the arc of the circle is. It's that set of points. And then arc length. Arc length we pretty much come up with the exact same way that we come up with the perimeter. Not the perimeter, the way, pretty much the same way that we talked about the circumference. So if I take some circle, some interior angle, like that, here's A, here's B, and then I bisect this angle at some point here, I guess we'll call that C, then I have this distance and this distance that I can add together, right? And maybe we'll call that length when we have two sides. And then for each of those sides, I could bisect it and make it instead go from here to here, and bisect this and make it go from here to here. So now we're talking about this length. and maybe call that L4. And then I could split each of those in half again, right? And call that L8, and then L16. And I could keep doing this over and over and over again, getting closer and closer to the exact length of this actual arc. Right? So we're going to define our arc length to be the limit of this kind of series. And then you might have to argue really quick that it has an upper bound by just picking some exterior point, like this. So now let's go over what he's actually saying. So that's a big idea. And then let's look for his definition. Okay, so he says pretty much the same thing. For every n, L sub n is less than L. Where does he define L? Some over bound. Some upper bound, not over bound. Oh well, let's just jump right to the definition. So definition 12-2. Given a circular arc, let Ln be the length of a regular inscribed polygon path. This is a regular polygon path because each of these were the same long. And remember, a polygon path is just a bunch of line segments that starts at one point and ends at another point. A regular polygon path is a polygon path where all the segments are the same long. Am I losing you?
You're saying that's a regular polygon path?
I created a bunch of regular polygon paths. So first I created a regular polygon path of 2, here to here, then here to here. That was a path from A to B, and it was regular because that distance and that distance were the same long by construction. And then I created a regular polygon path of length 4, not length 4, but with 4 segments. And then I can create a regular polygon path with 8 segments, and a regular polygon path with 16 segments. And I can keep doing this indefinitely, creating a regular polygon path from A to B, using as many sides as I want. And I'm calling the length of that polygon path, the limit of the length of that path is what this arc length is going to be.
Because that's the thing, it's getting closer and closer to becoming.
Yes, that's what our intuition is telling us. But this is a definition. We're defining the arc length, which I'll denote as L. We're defining it to be the limit of this series right here. So as this goes to infinity, whatever limit that approaches, I'm defining to be the arc length from A to B. So let me read the definition one more time. Given a circular arc, let Ln, meaning L2, L4, L6, A, L16, all the way to Ln, be the length of a regular inscribed polygon path of 2, 4, 8, 16, 32 sides, ... inscribed in the arc. The length L of the arc is defined to be the following limit. L equals the limit of L sub n. So does that definition make sense? Okay. Theorem 12.1. If in a circle 2 central angles are congruent, they subtend arcs of equal length. If in a circle, oh, so we're inside the same circle. So I guess we're going to start with just one circle. And that's probably just going to be a word, or let's show the picture to make sure you see it. So we're saying if inside of a circle, I have this central angle from A to B. There's O. And then we have some other central angle. Call that A prime, I guess, and that B prime. And if this angle is congruent to this angle, then this arc length is congruent to this arc length. Okay? Now, how would we argue that? We'd say, well, first off, make a triangle with just one side, and a triangle with just one side, and these two triangles are congruent. So then this polygon path is the same as this polygon path, so L1 equals L prime 1. And then bisect both those, so we make that L2 and we make that L2. So L2 is equal to L prime 2. Dot, dot, dot. So Ln is equal to L prime n. So the limit of this is the same as the limit of this. And so they're equal.
That's our definition for arc length.
Does that make sense? So we'll read what he says. Proof. Because the angles are congruent, the inscribed polygons at any stage are also congruent. Thus the lengths of the corresponding polygonal paths are the same. Hence the arc lengths are the same. I think it would have been nice if him to list out something like that. But oh well, I think you get it. Theorem 12.2. Let Pn be any sequence of polygonal paths inscribed in the arc AB of a circle. And let little ln be the sequence of lengths of these polygonal paths. Oh, so Pn is a polygonal path, Ln is their lengths. Let Sn be the length of the longest side of the path of Pn if the limit as Sn goes to 0. This is the same type of argument that comes up in high school calculus over and over again. What they're arguing here is that when, let me draw just one. When we were taking the limit of these polygonal paths, then we were always bisecting it into two, right? So let me draw kind of a big one. So there's the center O, here's A, here's B. We started by, use a different marker for how we're splitting this up, different color. We started by first looking at this one, and then we bisected that and split it into two. And then we bisected each of those, and we kept going like that, right? To get L1, L2, L4, L8, etc. Now what the author is going to come back around and say is, we didn't have to do this. We didn't have to bisect them perfectly each time. We could have split these up however we wanted, as long as our biggest piece of our polygonal path in our splitting up still went to 0. As long as we were still making our biggest one arbitrarily small, then this argument still works. You probably remember the same idea for integrals.
Yeah.
They say we can divide up the domain however we want, as long as our biggest delta x still goes to 0. And it's a stupid hand-wavy argument instead of just talking about partitions. And so, trying to think how to make this make intuitive sense. Basically, here's what he's saying. Instead of me drawing these dotted lines, I'm just going to draw the points up here, and then you can see it, right? So he was doing a point there, and then he was doing a point here and a point here, right? And then he was doing a point here and a point here and a point here and a point here, and he kept doing that, right? Notice as you keep doing this to infinity, the distance from here to the next point is getting closer and closer to what?
To the point.
What is this length getting closer and closer to from this point to this point?
Oh, 0.
0. And same with this gap. Every single gap is going to 0, right? And all these gaps are the exact same size. So what the author's saying is, as long as your biggest gap, which all of them are the exact same size, so we can call any of them our biggest gap, he says as long as your biggest gap is going to 0, then this still works. You didn't have to perfectly split them up. I could have kind of randomly stuck them in here, but I have to randomly stick them in such a way that my biggest gap still goes to 0. It is weird. I don't like the argument. Every time it comes up in a textbook, it bothers me. You're going to have the same argument if you take high school calculus from someone that's not me, most likely. So that's what he's saying. He's saying you don't have to use these specific points necessarily, but as long as your biggest gap's length goes to 0, then this limit still works. So we can pick any way we want of adding up those distances as long as the biggest gap goes to 0. And I can't think of another way to do it off the top of my head. It's easier with integrals to think of one. But anyways, so he's pointing that out. And he doesn't have a proof of that. Surprise. Yeah. Anyways, Theorem 12-3. If the arc length of AB and the arc length of BC, not their length. If arc AB and arc BC are adjacent arcs, that is, if they have only the point B in common, then the length of ABC is equal to the lengths of the individual arcs. And that we get just from the sum of the limits is the limit of the sum. So let's see what he's saying. So AB, and then we'll put a C up here. So these two are adjacent. And we're figuring out what AB, the length of AB plus length, maybe I'll do it this way. L sub AB, the length of this arc plus the length of this arc is what we're trying to figure out. So if these two are adjacent, meaning that these two arcs only have the point B in common, we're trying to prove that the length of this thing plus the length of this thing is equal to the length of this whole thing. Right? And we know what the length of this thing is. I'm not sure how to denote this. This length is the limit of some sequence, right? So that length is equal to the limit of some sequence L sub n. And this is equal to the limit of some sequence L prime sub n, I guess. Right? That's how we define the arc length to be the limit of some polygonal path's length. So are you good with going from here to here? And then one of our properties of limits is that the sum of the limits is the limit of the sum. Right? And if L sub n is always the length of a polygonal path from here to here, and L sub n sub prime is always the length of a polygonal path from here to here, then these two together are a polygonal path from here to here. Right? And then so that, once again, is going to equal whatever that limit is by definition, that thing's arc length. Does that make sense? Our whole argument there? I probably should have gone from lengths to polygonal paths and then argued a polygonal path from A to B and then from B to C is a polygonal path from A to C. Maybe I should have done that.
Wow, the length from A to C makes sense.
But, yeah, I thought you might be able to follow just from here to here. I mean, this is almost identical arguments to how we talked about perimeter.
Wait, does that
or
make
circumference.
sense? Okay, if you take the length from A to C is equal to the length from A to B plus B to C, you're counting B twice.
No, that's why I said we might want to go to polygonal paths. If I have some path, some polygonal path which goes from, good Judy, which goes from A to A1, A prime to A double prime, dot, 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 and finally gets to B. So there's one polygonal path. And then I have a polygonal path here, which starts at B, and then goes to B prime, B double prime, dot, 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 and eventually gets to C, then I can concatenate those two polygonal paths together.
Okay.
And then the length of these segments, and then the length of the new path is the sum of the lengths of these two older paths. That was a step I was saying we might need to make from here, go to the polygonal paths, then go to the new polygonal path that we get from putting those together to here.
Right.
But if you understand that, then we're good. Do you understand what I'm saying here? You do?
Mm-hmm.
Okay. And he does something very similar. Oh. So he just calls this one the limit of L sub n, L sub m prime, and L sub n double prime. But his argument's almost the exact same as mine. Oh, except for he goes backwards. He starts at the arc length of this, which is 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 the arc length of our two individual things. But basically same thing. So that was theorem 12-3. Alright, theorem 12-4. If in a circle one central angle is greater than another central angle, the greater angle subtends the longer arc. Yeah. So he's saying, let me just draw a new circle. I'm really sick of these colors not showing up good. Have I already tried blue?
I don't remember blue.
I don't think so.
So,
Green, black, red, and brown.
he's saying,
Nope.
let's just start throwing away everything that's not working for me. That green isn't doing great, that brown might be our best bet. Wow. Alright, being brown's my best bet. I need to remember to bring markers next time we come to this class. Or if I move the camera, just move over to the chalkboard. I don't want to take time to do that. Okay, so what he's saying is, if we have some central angle and we have some other central angle which is less than this angle, then this arc length is less than this arc length. Right? And how could we make the argument for that? Any polygonal path that we use here has its length. Then we add on a polygonal path here, which is going to add on some length, which a positive number plus a positive number is going to be bigger. Now we'll see his idea for it. What number was this?
12-4.
12-4. If in a circle one central angle is greater than another central angle, the greater angle subtends the longer arc. Proof. Since congruent angles, oh duh, that's another way to say it. Congruent angles subtend arcs of equal lengths, we may suppose that the central angles are as in figure 12-11. So that's not an argument I made. So I shouldn't have drawn it here to begin with. I should have said we're comparing this one A, B, C, D. So we're comparing this one and this one, and we know that this one is smaller than this one. So since this angle is smaller than this angle, that means that I can draw some ray interior to this angle such that this angle is congruent to this angle, right? And then since congruent angles have congruent arc lengths, this length and this length are the same, and then this length is this length plus this length, which is going to be bigger. So that's how he's going to say it, or something to that effect. Since congruent angles subtend arcs of equal lengths, we may suppose that central angles are drawn like this instead of having one down here. Draw one on top of the other, that's what he's saying. And that angle AOB is greater than AOC. He put a C there. Or COB, he put a C there. The remainder of the proof using Theorem 12-3 is left to the student. And Theorem 12-3 is saying,
Is that length?
the arc length from here to here is equal to the arc length from here to here plus the arc length from here to here. So we good with that? This arc length is greater than this. Well, this arc length is greater than this arc length. That's what we were saying. Because this is equal to that plus that. That is congruent to that.
So they just drew CD over B on the.
Yeah, they skip doing this there.
Why did you need to do the congruent piece though?
So here's what we're proving. If in a circle two central angles, if in a circle one central angle is greater than another central angle, the greater angle subtends a longer arc. So all I know is I have two angles where one's greater than another. I don't know that they overlap in any way. So I've got one angle and another angle. All I know is that this one is bigger than this one. Since this one is bigger than this one, then I know I can draw one interior to here congruent to this one. Right? So I know that, let me give this point a name. A, B, C, D, E. I know that arc length AEB is equal to AE plus EB by the previous theorem that we did, right? And I know by another previous theorem that we did that congruent angles have congruent arc lengths is equal to AE plus CD, which is what I want to show. I want to show that this is greater than this.
So we started with CD, made EB congruent to CD.
Okay. How's 12.4? 12.5. Converse to Theorem 12.4. So the converse to this theorem is going to be to go the other way. If I know that one arc length is greater than another arc length, then I need to show that its angle is greater than the other one's angle. Does that make sense?
So instead of saying that angle is less than, you're saying it's greater than?
So this one, I use the fact that angle AOB was greater than angle CD to prove this. Now I need to show that if AEB is greater than CD, then angle AEB is greater than angle AOB is greater than angle COD. That's the converse of that theorem. So now we need to go from, we know that this arc length is bigger than this arc length, 2, this angle is bigger than this angle.
Can we construct congruent arc lengths?
I think we want to use the contrapositive of one of the theorems we already have. We know that congruent angles implies congruent arc lengths. So not congruent arc lengths implies not congruent angles. Well, that doesn't give us greater than or less than.
One is greater than the other, but it doesn't say which.
Yeah. Let's see, what's another idea?
Wow, we could use the contrapositive of that other theorem and then apply 12-4. Wait, can you look?
The contrapositive of which theorem?
Of which theorem? Of the one that gives us an inequality. And then apply 12-4 to it.
I don't know what you're talking about.
The one that tells us that the angles are different. Central angles are not congruent. They do not subtend that to be equal.
Oops. So maybe here's the way to do it. If AB is greater than CD, then we can argue that there exists some point E such that AEB, it's between them on the arc, and AEB
Or
EB
to CD.
is congruent to CD.
So similar to our other group, just
Right? That's what it means for this to be greater than this. And then let's see if that is congruent to that. Right, I need to say that the angles are congruent. Oh, here's how we can argue it. We'll just use this theorem over and over again. We say, look, if this angle is greater than this angle, then this side has to be greater than this side by this theorem. So we say, if angle EOB is greater than angle COD, you with me so far?
So you're
Right.
their contradiction.
Right.
Okay.
If this angle were greater than this angle, then we know that this EB, that length, is greater than CD by this theorem. This theorem says if this angle is bigger than this angle, this arc length is bigger than the other one. Which can't be the case because we know those are congruent. And then if it's less than, then I can flip it so that one's greater than and do the exact same thing. So they have to be congruent. Do you see the flow of the argument there?
Yeah.
Right? So my next one would be if angle COD is greater than angle EOB, then CD is greater than EB, which is again a contradiction. And so this one's not greater than this one, and this one's not greater than this one. Then they're congruent. Then angle EOB is congruent to angle COD. Then angle AOB is greater than angle COD. You see the flow of that argument?
Yeah.
Okay, so I think that's the way to prove that. Theorem 12.6. Two central angles of a circle are congruent if and only if they subtend arcs of equal length. We've already proved that one way. If the angles are congruent, then the arcs are equal length. And then when you just barely did right here, if the arcs are equal length, then the angles have to be congruent. That's just this piece of this proof. So maybe there's an easier way to do this proof than that, because this problem comes after. So we're probably missing something obvious for proving that, but what we did works. All right. Arcs on different circles. Need water. Arcs on different circles. Theorem 12-7. If arc AB and arc A prime B prime are arcs on two circles of radii r and r prime respectively, and are subtended by congruent angles, then the arc lengths are proportional to the radii. That is, if those angles are congruent, then that over that is congruent to that over that. Okay, so let's construct that argument. So we're saying if we have two circles that aren't necessarily the same size,
Aren't all radii proportional to each other? Because all
it
circles
doesn't
are
make
similar?
sense for a radii to be proportional to each other. You need four numbers to come up with a proportional.
Oh, yeah, I see.
Like, so one of the things that we just barely proved before you got here is that when you have two circles, one circumference to its diameter is equal to another one circumference to its diameter. So if I take this thing's circumference divided by its diameter, it's equal to this thing's circumference divided by its diameter. Which you already know what that is, right? Pi.
Mm-hmm.
That's the same for all circles. But it doesn't make sense for me to just say this thing's diameter is proportional to this thing's diameter. That statement alone doesn't make any sense. Okay. So it's the same if we have two circles with radius r and radius r prime, and we have some central angle A, B, and it's that big, and then down here we have A prime, B prime, but this angle is congruent to this angle, then we're trying to show that the ratio of AB, that thing's arc length, to R is equal to A prime, B primes to R. If we know that these two angles are congruent.
Okay.
Right? Lost my page. 215. Okay. So, let's think about how we get this arc length and this thing's arc length. And let's think about those two series. So, first off, what's the right way to say this? We'll construct the series for this one's arc length, and that's going to be, so we'll say this one is going to be L, and it's going to be the limit of the series, L sub n, and we'll call this one L prime, and it will be the limit of the series L prime sub n. So this right here, this length will be L1, and then this seam's length right here will be L prime 1. And then when I put a dot right in the middle and I do this, then that will be L2. Similarly down here, that'll be L prime 2, and then I'll continue. So that's how I'll create these two series. You understand what I'm saying?
Yeah, I understand.
Okay, so notice when we do L1 and L prime 1, this is an isosceles triangle, right?
Yeah.
So this angle is congruent to this angle. And then this is going to be a similar triangle to this one. It's also an isosceles triangle. And since that angle is the same as that angle, then this angle and this angle are also going to be the same as those triangles, right? So those are similar triangles. So I know that L1 is proportional to L prime 1. I know that their side lengths are proportional. So this side length right here is R, and this one's R prime, right? Maybe that's where I should put it. So I know that R over R prime is equal to this. You with me there? Similar triangles, sides are proportional.
Right.
That's what needs to be similar. And same with L2 over L prime 2.
Mm-hmm.
And so, in general, L sub n over L prime sub n. With me? So, the limit of R over R prime is equal to the limit of Ln over L prime n is equal to, well, we'll just rewrite it. This gives us, implication arrow, the limit of a constant is just a constant. Right? What does R approach as n goes to infinity?
It's just R.
Just R. It doesn't change. No matter how many times we split this up, the radius of our circle is still R.
Right.
You with me?
Yeah.
So that still is just R over R prime. But now what's the limit of this distance? That's this and this, right? That's the arc length. So maybe L or L prime, we're kind of been using bad notation. I've been using this to talk about a length instead of saying the measure of that. Because this is really the set of points. Right? The same way that AB is a segment and then that means the length.
Right.
This doesn't mean the length. This means the actual set of points. And I've been talking about like a length, which is bad.
Okay.
So sorry about that.
What would you use to say the length then?
Huh?
What would you use
You
to
draw
say
a straight line.
So
over
L is the length of that and L prime is the length of that.
Oh, I see.
Or you just write the measure of this. So is equal to L over L prime, right? When we take the limit of this thing over here.
Yes.
So that's how you show it, right? Is that what we were trying to show? Let's read it one more time. If arc AB and arc A prime B prime are arcs on two circles of radii R and R prime respectively, maybe get rid of these because we marked the radius right there already, just mucking up our picture. And are subtended by congruent angles, so that angle is congruent to that angle, then the arc lengths are proportional to the radii. That is, the length of AB. Oh, I did different than he did. So here's what he wanted to show. He wanted to show, and then I'll even write how he says. He said the length okay. So here's what he said we're going to try and show. Now I wrote this as L and this is L prime, right? So I'm trying to show that L over L prime is equal to R over R prime. What did I show? I showed R over R prime equals L over L prime. Oh, I did show that. Why did I think I didn't?
Well, there's the other one that says the length of arc AB over R equals the length of arc A prime B prime over R prime.
Oh, did I write this different than him?
Well, he has two. He has both of those.
Oh, maybe I kept seeing one and then the other and thinking I did different than him. Yeah, and you know how to go from this to the one he has, right?
Well, it's the same thing basically.
Yeah, it is the same thing. You can swap those two and it's the
Yeah.
exact same thing. Okay, so we won't worry about it. So that was Theorem 12.7. And he gave a much more wordy proof. Of course, I didn't give any words. Maybe my word been as wordy as his. If I would have written all that out. Okay. Theorem 12.8. Suppose that L is a positive number less than or equal to 1/4 of the circumference of a circle of radius r. That is, L is less than or equal to pi r over 2. Pi r over 2 is 1/4 the circumference of a circle. What's the circumference of a circle? 2 pi r. Take 1/4 of that, you get pi r over 2. Right? So that's not a multiply by, that's a side note. He's not saying r times that. Are you reading in the book?
I'm trying to follow what you're saying.
I'm saying in the book he has r and then parentheses, L less than or equal to pi r over 2.
Right.
He's not saying times there.
Yeah, he's saying over, right?
No, he's saying
Yeah, there are.
suppose L is a positive number less than or equal to 1/4 the circumference of a circle of radius r. In other words, L is less than or equal to pi r over 2.
Yeah.
So that's not a mathematical expression,
Oh, I see.
is what I'm trying to clarify. Because that looks weird to me that he wrote it there. He should have put a comma and said, in other words, and then wrote that. Then there is an arc of the circle whose length is L. Okay. So he's going to have to make a very specific argument for this anyway, so I don't care about this proof. But let me go over the idea and let's go over not the special case that he's doing, but it in general. Here's what he's saying in general. If you pick an arc length less than or equal to the circumference of a circle, then there is an angle that will give you that arc length.
That's like the whole circle.
Give me any arc length less than or equal to the circumference of the circle,
Oh. Okay.
then I can give you the angle that gives you that arc length. I guess I have to say less than the circumference of the circle. It can't be equal
Yeah.
to. You're right. Because an interior angle means two distinct points. So that's what he's showing in general. And he was doing a special case with 1/4 the circle and then working his way up to give you the intuition from there. And even in showing it with 1/4 the circle, he's only going to pick special numbers to show it. Because it's not an easy thing to show in general. So it should make intuitive sense though, right?
Yeah.
What is arc length measuring? It's measuring some portion of the circumference, in other words. And so it can't ever be more than the circumference. And, well, it's saying more than that. This is basically like the completeness axiom that we had before. So if you remember what the completeness axiom said, for this class, it says, pick any number you want, and I can create a line segment that long. That's what it said. Now we're saying, pick any number you want that's less than the circumference, and I can find an arc length that is that long. That's what it's saying. Okay? Does that make sense?
Yeah, but what if it was more? Could you have an angle greater than 360, like in geometry?
So right now we don't have the idea of an angle greater than a straight angle. The largest angle we can make is a straight angle. You can't make one bigger than a straight angle with how we have it right now.
Okay.
Because when we're talking about an angle, this is why I didn't like him introducing degrees so early in the book. When you hear angle, you want to assign degrees to something, and you want to talk about some number of degrees, and you're real comfortable talking about 720 degrees. That's fine, and you think about that in your head as going around the circle twice. But what is an angle, geometrically speaking? An angle is two rays that meet at a vertex. Two rays coming from the same vertex. That's what an angle is. So you don't get to say, pretend that this goes all the way around like this with some sort of weird movement. You just get to draw two rays coming from the same origin. That's it. That's all you get to do. So I would say draw a 270 degree angle. You might be tempted to draw something like this, right? Oh, there you go. Well, by our definition, that's less than a straight angle. The biggest angle you can make is a straight angle.
Okay.
Now, when we come to definition of degrees, I'm not sure if this book will bother working its way up to how it's going to go about arguing that. But when so far talking about angles, the largest angle is a straight angle.
Yeah,
We said that this angle is greater than this angle. Because we don't have a notion of talking about. Now, when I do this thing, I talk about from here to here. Because an angle is just that set of points. That's it. That's all it is.
Mhm.
So it's really a simpler idea than degrees.
Right.
Right. Okay. So, measurement of angles. Okay. So now we're going to just talk about what a degree is. And arbitrarily, we're going to, well, let's just read the definition real quick, and then we'll have this conversation. Definition 12-3. On a circle of radius r, an arc length of 1/360th times 2 pi r is subtended by a central angle of 1 degree. So if I have this circle with radius r, what's its circumference? 2 pi r, right?
Yeah.
So if I take 1/360th of 2 pi r, I take that length and I mark out the arc length of that and create a central angle with that arc length,
Oh, I see.
then this is 1 degree. Does that make sense?
Yeah.
Remember what the previous theorem just really said. The previous theorem says, for any length you pick smaller than the circumference, I can construct a central angle that has that length as its arc length.
Yeah.
Right? So now we just came up with a definition for a degree. That's what 1 degree is. It's you take the angle, the central angle, that subtends this arc length. That's a degree. Now, why on earth is that the way a degree is defined?
No, I knew.
Is that not just the most random bunch of nonsense you've ever seen? 1/360th of that number, and we're going to call that a degree. Why not 1/100th of that number? Or 1/1000th of that number? Maybe split the circle up into 4 quadrants of 100 degrees, maybe. So it's 1/400th of that number. Why the heck is it 1/360th of that number? Because it makes math real nice, right?
Yep.
Because you're used to it, and so it's nice. No, the real reason comes from, I think it was the Sumerians. They used a base 60 system when they counted. We use a base 10 system. What do we mean by a base 10 system? We mean every multiple of 10, you add a new digit. I can count 10 numbers only using one digit. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? I can count 100 digits. I can count 100 numbers only using 2 digits. 0 through 99. Every multiple of 10 I go up, I need a new digit. They did it in 60s. So they had, well, I don't think they had a 0 idea yet. But when they got up to 60 is when they would bring in their next digit.
Do your countries still do that? Like, do they do mathematics?
They brought in
I don't think that it is common anywhere to not use a base 10 system. Math is now so standardized. But mathematics developed in many ways independently.
They have one digit to go to 60.
Yeah. Well, the 59.
They have 60 different symbols.
Well, I think they only had 59. Because I don't think they had a 0. They would just shift places. So instead of writing
They'd shift one.
50, they would write their symbol for 5, and then it would be understood like there's a slot there. It's weird doing, like, a lot of the class I have to do is history of math. And you do math the way that ancient civilizations did math, like the way the Egyptians did math. I don't remember which is which, but doing math in those different systems is hard. And it's a class that they specifically require, not for me, I was a math major, but if you're in math education, they require you to do it. And the reason they require you to do it is they want you to understand how arbitrary it is when you're teaching some kid the rules that we use. Because they're completely arbitrary. Why do we use 10 instead of 60? Why did they use 60 instead of 10? It's completely arbitrary. There's no universal reason why we should count the way that we count. And we have all sorts of rules that we use just because that's the way we use them. And the way we like to think about it is the way we like to think about it. And the way the Egyptians like to think about it is the way the Egyptians like to think about it. And you try doing math their way, and it's a pain in the butt. And they try doing math your way, and, well, they don't have that opportunity because they're long gone and dead. But you can try to do it the way that they did it. And so they require you to do it so you can relate to that kid and see what level that kid's on, where you're telling him all these things, and the kid's just thinking, wow. And then you're going to tell him, because that's the way we do it. Now, hopefully you'll have their reason. But anyways, completely arbitrary. It's just the way it's been done for so long. And then we go further than that, thanks to these Sumerians. 1/60th of a degree we call a minute, and 1/60th of a minute we call a second. You've never seen that before?
1/10 of a second, you call that.
We don't have tenths of degrees, we have 60ths of degrees. And we don't have hundredths of degrees, we have 3,600ths of degrees, which we call seconds and minutes. And it's also the same reason that we say that there's 60 hours in a day, or 60 minutes in an hour, and 60 seconds in a minute. Once again, good old Sumerians. Completely arbitrary. Now, one of the reasons that we think they picked the number 60 is because it's a very divisible number. 60 is divisible by 2, 60 is divisible by 3, 60 is divisible by 4, 60 is divisible by 5, 60 is divisible by 6. 10, what's 10 divisible by 2 and 5? Big whoop. 60 has 2, 3, 4, 5, and 6.
And
Real easy to divide by those. And 10. And 12. And you can keep working up with the different multiples of what we've already said. Right? So that's the reason that they think that they chose it. And if you think about it that way, maybe that makes more sense than our base 10 system. Our base 10 system, when I tell you to divide by 3, it's a pain in the butt. In a base 60 system, anytime you have to divide by 3, it's not fast. Right? Right. Okay. So that's the definition of a degree. Completely arbitrary. It is what it is, completely for historical reasons. Okay, notice remark number 1. The definition of a degree is independent of the radius. In other words,
Yeah, but you need the circumference.
Well,
No.
it's the angle
So
that
it
subtends.
it's the angle that subtends 1/306 with this as its arc length.
Arc. You're right.
So for any circle you pick, this is still the formula that you would get for its arc length.
Mm-hmm.
Comes out the same every time. 1 degree is 1 degree is 1 degree. Does that make sense?
Yeah. 1 degree is 1 degree.
In other words, if I were to double the size of the circle, the arc length subtended right here is still 1/360 times 2 pi times r.
Yeah.
And if I were to shrink that circle down really small, that arc length is still 1/360 times 2 pi times r. That's what he's trying to say. Remark number 2. Any angle congruent to angle 1 or to an angle of 1 degrees is also a 1 degree angle, right? If I have some other angle that's congruent to that angle, we already have a theorem that means its arc length is congruent to this arc length, and therefore it's 1 degree. So if this angle is congruent to this angle, they're both 1 degree angles. And similarly with 2 degrees and 3 degrees and whatever. Right. If on a circle of radius r, a central angle subtended by arc length If on a circle of radius r, a central angle subtends an arc of length L, then the measure of the angle in degrees is L times pi r times 180. Okay, let me simplify this one more time, and then you'll see what he's saying. So we can rewrite this as pi r over 180, with the 2's going out. You see that?
Yeah.
So now what he's saying is, if we have some arc length of L, so I know that from here to here is L, and I want to know what that is in degrees, he's saying that, we can keep an R there, but let me name this angle. Angle 1. He's saying that angle 1 in degrees is going to equal L divided by, we're going to take the reciprocal of this, pi r times 180. Now, let's make intuitive sense of this first, and then you'll see this equation. Just think naturally how you would do this. If I said, this distance is L, and I asked you what portion of the circle does L take, how do you figure that out? You would do L divided by the circumference, right?
Yeah.
Yeah.
L divided by circumference tells me the portion of the circle that takes,
Mm-hmm.
right? Well, L divided by the circumference is going to be L over 2 pi r, right?
Mm-hmm.
Now finally, if you want to convert that to degrees,
You have to use.
you're going to multiply it by 360, right?
Yes.
So in other words, if this is 1/4 the circle, then it's 1/4 of 360 if you want in degrees. Do you see what I'm saying? Am I losing you?
No, that's why it's times 180 because you took away
Right.
the radius.
So then if we want to get this to degrees, we need to multiply it by 360 degrees, and then the 2 and the 360 cancel, leaving us with this.
Mm-hmm.
So that's another intuitive way to see it. Or you could see how's the way to say that? Let's see. 1 degree is pi r over 180 trying to think of an intuitive way to say that other than what I just walked through. Let's see if the author does it, see if he gives us a better way to think about it. If on a circle of radius r, a central angle subtends an arc of length L, then the measure of the angle in degrees is L over pi r times 180. So that's the ratio of the circle that takes times however many degrees are in the circle, is what you would do here. But then those two cancel out, which is how this comes about. I think that's the best way to get intuition for that. Does this make sense what I'm talking about over here? Okay. Remark 1. This definition agrees with definition 12-3 for an angle of 1 degree. So let's think about this for an angle of 1 degree. So by definition, so we're saying an angle of 1 degree by definition has length this, right? So I'm plugging this in for the length. By definition, 1 degree has length equal to this. That's the definition of 1 degree, right? So I'm going to plug that in for L up here, and I better get 1 when it's all said and done. So plugging in L there, we plug in for 1 degree, pi r over 180 times 180 over pi r, which equals 1. So I plug in the length there to this formula, and it spits out my angle in degrees, which for 1 degree better have come out 1, and for L in general will be whatever it comes out to.
How do you get more than 1?
Plug in whatever your arc length is. Here's the arc length for 1 degree. In general, plug it in here and you get out your angle. This wasn't an angle of 1, this was just some angle that I called 1. Maybe call that, I don't know.
So if you have the measurement of your arc, that's how you would find the degrees.
Yeah.
Then you can find the angle that's
So let's do another one real quick. What's another angle that we know right off the bat? What if I use an arc length of pi halves? Pi halves gets me 1/4 the circle. 2 pi gets me all the way around the circle. So what's 1/4 of 2 pi? Sorry, 2 pi r. I was missing my r. I was thinking about unit circle. What's the circumference of a circle?
2 pi r.
Okay, so let's plug that in. We better get 360 degrees, right? For our length.
Yeah.
If my length is the circumference, I better get 360 degrees. Let's try it. So plug in 2 pi r for L over pi r times 180 equals, pi r cancels out 360.
I see.
Let's try another one. For a fourth of circle, what is the arc length of a fourth of circle?
1/2 pi r.
Yeah, pi r over 2. So if I have pi r over 2 over pi r times 180, that equals 90. Pi r goes out with pi r and we have 1/2 times 180. Top of the bottom goes into the bottom of the top. Those cancel out, leaving 1/2. You can think about that as pi r over 1 if you want.
Okay.
So it works, right? Counting degrees. Oh, did we talk about the last one? If m is the measure of a central angle in degrees, then the length is m times pi r over 180. So
length from angle.
this takes us from length to, they're using m for the measure of the angle. So the measure of the angle equals length over that. Or in other words, if I know the measure of the angle, I can figure out the length. Length is equal to m pi r over 180. where m is the measure in degrees. Should we try one real quick? What happens when you plug in 360 for m? What's 360 divided by 180?
2.
You get 2 pi r. 2 pi r is the length when you plug in 360 degrees for the angle.
Right.
You plug in 180, you get pi r, which is half. You plug in 90, you get pi r over 2, which is 1/4,
Right.
etc. So this gives you degrees when you know the length. This gives you length when you know degrees. And you also need to know the radius of the circle, obviously. Right?
Yeah.
Okay. Okay. Theorem 12-9. Suppose that angle AOB is an acute angle, and we consider successive arcs subtending central angles of 1 degree on the circle from B to A, so that the point A is a point of the n plus first arc. Then the measure of angle AOB in degrees is either equal to n or n plus 1, or is in between n and n plus 1. Okay. That's pretty obvious, right? Do we need to go over that? Do you understand what they're saying? They're saying if you have some angle, we're going from B, here's A. Okay? And from B to right before A, that is n degrees. And then to past A, that is n plus 1 degrees. Then A, the angle A is in between n degrees and n plus 1 degrees.
The angle A?
Yeah, so an angle of n degrees from B takes me from here to here. An angle from B of n plus 1 degrees takes me from here to here.
Yes.
That means the measure of angle AOB is between n and n plus 1 degrees.
Oh, I see.
That's all it's saying. And then the second thing that they're going to prove right after that, using the same idea, is if two angles are congruent, they have equal measure. So we said if they have equal measure, then they're congruent. If they're congruent, then they have equal measure. Oops, did I say that backwards?
Why do you need to prove that to prove this?
She's talking about how you measure an angle.
Oh, we already did that. My page turn. Theorem 12-9. Yeah, that's this one. Theorem 12-9. If this is n degrees and this is n plus 1 degrees, then that angle is between n and n plus 1 degrees.
It could also be on n plus 1 or on n. Or no, it couldn't be on n, but it could be. Oh,
No,
I guess it
because it
can
goes
be on n
past.
plus 1. There's
You
three
go just
cases.
before A,
There's
and
three
then you go
cases.
after A.
Either it lands right on a degree. There's two cases. Either it lands right on a degree or it lands between 2 degrees.
Yeah, so it's the same argument that we've been using for making,
Numbers.
measuring
Length.
length. When I was measuring length, I went along and I said, so I want to measure the segment AB. Here's the big idea that I was trying to capture with the theorem, so let's just talk about it. When I'm trying to measure AB, I have some unit length, in our case it's 1 degree. But when I'm trying to measure AB, I have some unit length, maybe it's 1 inch, right? What do? I come off and I go 1, 2, 3, 4, 5, 6, 7, and I keep going until I get past that. Till this interval contains it,
Right.
right?
We're supposed to do the same thing.
So either I land right on it and I got the measure of my angle, or I go past it and now I need to zoom in on this and do it again.
Right.
So he's saying we do the same thing, counting off 1 degree at a time until we get past it. And then so we're either going to land right on it or we're going to go past it. When we go past it, we zoom in on this thing, we split it up into 60ths, and we do it again to get minutes. And if we don't get it perfectly when we do it in minutes, we can zoom in, split it to 60ths again, and do seconds. And then that's the most fine I've ever seen it measured, unless you do decimal numbers after that.
We did that in physics. Decimals of seconds.
Oh, we did?
We had to.
Wouldn't a second be a decimal?
No.
Huh.
It's 3,600th of a degree. It's like doing 2 decimal places, except for base 60. So you have 60th and 3,600ths. Instead of tenths and hundredths, you have 60ths and 3,600ths.
It's like meter, centimeter, millimeter.
So would you write it like that?
So when you write it, it would be 32 degrees, 3 minutes, 6 seconds. Or 31 minutes, 17 seconds. I bet you've seen that before and you just don't remember.
Probably.
I don't think I saw that until trig. What grade are you in?
I think you get that. You gotta switch over from Saxon math. Pretty sure Saxon math does that for algebra.
Yeah, but I've been in Pearson for 3 years.
You've been what?
Does section, doesn't
No.
Pearson. That's what it says. Yeah, I don't know how Pearson does it. I didn't do that program. Okay, so now let's talk about another unit we can use. So, using a unit of 1 degree is pretty random, pretty arbitrary, right? And we use it for historical reasons. There's another way that we measure angles, which is far more convenient for math, and it is called a radian. Now, instead of, so how did we say what a degree was?
it? The angle that subtends that arc length.
We come over here, we take an arc length of 1/360th of 2 pi r, find that arc length, find the central angle associated with that arc length, and then we say that's 1 degree. All right? A radian, so much nicer. We say, come pick an arc length that from here to here is the same big as the radius, r. And then call this 1 radian.
Radians are super cool.
Do you have like only a certain amount of radians in a circle?
Yeah, how many radians do you have in a circle? Another way of asking that is how many radiuses does it take to get around the circle? What's the circumference of a circle?
2 pi r.
How many radiuses do I need to get around the circle?
2 times pi.
2 pi. That's how many.
Times pi.
2 pi. This is a number. All right, let's get comfortable with the fact real quick. We've probably already had this discussion in this class once, but let's have it again. If you go talk to one of your little siblings who's finally learning how to do division, and you ask them what's 4 divided by 2, they say it's 2, and they can tell you that. And then you come along and you say, what's 5 divided by 2? They say it doesn't work. It's 5 divided by 2. And you say, no, it's 5 halves. And they say, what? No, you just wrote 5 divided by 2. You didn't tell me what the number was. You said, yes, I did. It's 5 halves. And then eventually they grow up and they finally get comfortable with 5 halves as a number. That's okay. We can write 5 halves. We don't always have to deal with things where we can write it as just one whole number. And then you come along and you learn how to do square root. And I say, what's the square root of 9? You say 3. I say, what's the square root of 16? You say 4. I say, what's the square root of 2? You say, you're cheating. You can't do it. Square root of 2. I say, yes, you can. It's the square root of 2. You say you didn't do it. You got to figure out what that is. You can't just write that. I say, no, that's a perfectly fine number, just like 5/2 is a perfectly fine number. And eventually you get comfortable with the idea. Okay, you can write square root 2. Then you have to learn radians. And I say that there's 2 pi radians in a circle. And you say, what do you mean? 2 times pi? You got to figure out what that is. No, 2 pi is a perfectly fine number. It's just 2 pi. It's not 6.28 blah, 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 blah. No, that's some approximation. It's just 2 pi.
6.283, yeah.
Don't make it hard for yourself. It's just 2 pi. How many radians are there in a circle? There's 2 pi. How many radiuses does it take to get around the circle? 2 pi.
Okay.
How many radians in half a circle?
Pi?
Pi radians. That's exactly right. How many radians in a fourth of a circle?
Half. Pi.
Pi halves. Right?
Yeah.
There you go. That's radians. That's the normal, natural way. I should say normal or natural. This is the way that we measure angles that isn't dictated based off of,
Degrees?
no, off of some random inheritance. Why are there 60 seconds in a minute? Because that's the way that people who lived 5,000 years ago measure time. And so everyone's done it ever since. This one is, we chose this. This isn't something that we inherited. So this is a very natural way to talk about angles. And as you go further and further in math, this is the way you're going to want to talk about it. This is such an ugly definition for our base unit. This is a far better definition for our base unit. Just because it ends up having pi's in our numbers, that's no problem. And it makes it real easy to do things back and forth. Right? One example. If I tell you that this is an angle of 1 radian, then what's this arc length?
It's the radius.
It's just r. Right? If I tell you that this angle is 2.5 radians, what's this arc length?
Just
2.5 r.
Yeah. 2.5 r.
If I tell you that this is 175 degrees, what's the arc length?
175.
No, you gotta plug in 175 to this stupid thing and get some number out of it. You see how ugly that is to go back and forth?
Yeah.
That's why we love radians so much. Is you can go from talking about arc lengths to talking about angles like that. How do you go from the angle to the arc length? You multiply by the radius. That's it. If this is 2 radians, then the distance from here to here is 2 radiuses.
Right.
If this is pi radians, then the distance from here to here is pi radiuses. Pi r, whatever r is. Same for all circles. If your circle has a radius of 1, it's just pi. If your radius has a circle of 2 feet, it's just 2 times pi feet. 2 pi feet, right? So it's really nice, really natural way to measure angles. By the time you get to trig, this is going to be the way that you're always going to want to talk about angles. Real easy for us to do math with these things. Degrees are ugly. You'll learn to hate them.
Probably.
Hopefully. Means you went far enough. Alright. So that's radian. Well, let's read it actually. An angle of 1 radian is one which subtends an arc of length r on a circle of radius r. The measure of an angle in radians is equal to L over r, where L is the length of the arc subtended by the circle of the radius, right? So instead of having to memorize these things, how do I go from my arc length to my angle? Divide by r. Take that, divide by r, that gives me that.
Mm-hmm.
How do I go from my angle to my arc length? Multiply by r. That's all I have to do. Divide by r, multiply by r. You don't have to remember multiply by pi r divided by 180, or divided by pi r multiplied by 180. This is how you do it with degrees. We didn't write it for radians, but for radians it's just L equals pi r, M r, or M equals L over r. Much better. Much more elegant. And of course you can make up your own base unit. This could be your base unit. We could have our base unit as a radian. You can make up your own base unit to be half a circle. You can make up your own base unit to be whatever you want. Those are just the two normal base units that we always use. Angles and radians. Or sorry, degrees and radians. Good? And then, finally, the coolest theorem in this chapter. All this other stuff has been talking about the measures of angles. So this is theorem. My book keeps changing. Oh, and he splits out the special case into a lemma. We can do that. That's fine. So we'll start out with the lemma, do how he does it. Lemma. You know what a lemma is?
Why have I heard it before? I don't know what it is.
It's like a
Sounds
small
kind of like
proof
it.
for big proof.
So we have three different words for a theorem. You know what a theorem is?
Yes.
Okay. We have three different words that are theorems. We say lemma, we say theorem, we say corollary. A lemma is a small side proof that's trying to help me with my main proof, right? So if I give you a homework problem and I say prove this, and you have to keep like inside your proof doing small proofs over and over again, you might say lemma, here's a small proof, and then keep using your lemma over and over again as you do your proof.
Oh, I see.
That's what a lemma is. And then a corollary is something that's almost just like a special case of your theorem, or it almost immediately falls from your theorem. It's like almost no extra work. So, like one I was just proving today, I was showing that negative a times negative a is equal to a squared. And then my corollary for that was that negative 1 times negative 1 is equal to 1. And all I had to do was add the special step 1 squared equals 1. Because this is a special case of this. So it was a corollary because it took almost no work once I had this proven to show this. Does that make sense? That's what a corollary is. Okay. So our lemma is going to be, should probably keep that in. Well, first off, let's say what the theorem is, and then we'll prove our lemma. Then we'll go back and prove the theorem. So our theorem is the measure of an inscribed angle in degrees is equal to 1/2 the degree measure of the arc it subtends. So what do we mean by that? We mean, maybe I'll draw my picture over here and put my words over. If I have some circle, and if it inscribes an angle, that means all 3 points on the angle are on the circle. So that means I have some angle like this. Here's an inscribed angle. We're saying the degree measure of this, if I call this M, is, so here's my central angle that I would make with those same points, right? Here's the center of my circle. If this angle, or this angle we get from this subtended arc, is M, then this angle is 1/2 M. So if this was 100 degrees, then this angle is a 50-degree angle. Okay? So our corollary is, let's handle the special case where this line goes through the origin. So let's show that real quick. So let's say we're trying to prove this. Here's O. Let's pretend that this side actually goes through the origin. Here's B. Here's A. So we have this angle, I guess I'll call it point C. We have angle ACB. We're trying to show that that is 1/2 of angle AOB. Right? We're showing a special case that we'll show in general. That's not necessarily a right angle. Maybe I should try and make my picture not misleading. Let's put my A over here more. Good? So I'm trying to show that this angle is twice that angle.
Okay.
Okay? Now, first off, looking at this triangle, it's what?
It's a right triangle.
It's not right. That's bigger than a right angle.
Oh,
That's why I moved my A. I was afraid that that would look like a right angle.
okay.
But what do I know about this triangle?
It's an isosceles.
It's an isosceles triangle, so what do I know?
That CO is compared to OA. And that the angles.
That this angle is compared to this angle, right? That's what you're saying?
Yeah.
Now-
That angles the.
Oh, sorry, I should do 2 lines since I did 1 here. Now, this angle plus this angle plus this angle is a straight angle. And this angle plus this angle is a straight angle. So this angle is equal to the sum of these 2 angles. Do you see that? Maybe instead of putting tape marks, I'll label my angles. So we'll call this angle 1, angle 2, angle 3, angle 4. So I know that angle 1 plus angle 4 is equal to 180 degrees, right?
Yeah.
Or sorry, angle 2.
So, yeah.
And I know that angle 1 plus angle 3 plus angle 2 is equal to 180 degrees.
Yep.
So I know that angle 2 plus angle 4 is equal to angle 1 plus angle 3 plus angle 2.
Yes.
So take away angle 2 from both sides, and I know that angle 4 is equal to angle 1 plus angle 3. But I know that angle 1 and angle 3 are congruent, because it's an isosceles triangle. So I know that angle 4 is equal to 2 of angle 1,
Yes.
which is what I was trying to show.
Okay.
This angle is half this angle.
Oh.
You see that?
Yeah.
Okay, so now when we have the case where it doesn't go through the origin, so that was his length. So now when we have the case where it doesn't go through the origin, there's the origin. All we do is we split this up into 2 that do go through the origin. Right?
Okay.
So now I know that this angle is half of this angle, and I know that this angle is half of this angle, therefore this whole thing is half of this whole thing.
That makes sense.
And then if finally, it's the same exact argument almost, but if it was like this, and now the center of the circle is outside of it, we still imagine going through the center of the circle, and I know that this angle is half of this angle. Ooh. Let me think. Oh, we're gonna have to do some work with that.
Why? The full angle is half of.
We're trying to show that. Let's get rid of this dotted line for a second. Let's keep track of what we're trying to show. We're trying to show that angle 1 is half of
A, B? Yeah.
that angle.
Right, so draw a line through the origin. Call that point C.
So you're you're saying draw this line, call that point C.
Then you have angle A, initial point C,
Angle A,
or A. Yeah, you have A, angle A, initial point C is half.
oh,
have our
I
small
call this
angle.
O. Shoot. We can't call that O.
Oh, D.
D.
You have ADC is half of AOC.
ADC is half of AOC, yes.
And then you have AD. You have
Oh,
BDC.
I see what you're
half
saying.
of BOC.
BDC is half of BOC,
And then
and
you just subtract.
ADB is half of AOB.
Well, that's what you get from it.
Okay. So how do we know that it perfectly splits it like that? It has to. Okay, yeah, it has to. Right? This angle has to be double this angle. And this angle has to be double this angle. Therefore, this angle has to be double this angle. There we go. Does that make sense? Let's go. Let's draw out the actual algebra for it. So, angle.
I want to just label your angle.
ADB.
Yeah, that probably would have been better. We'll just stick with it. Angle AOC is equal to 2 angle
ADC.
ADC.
ADC. Thanks.
And angle
And then-
BOC.
Angle BOC is equal to 2
BDC.
of angle BDC.
We know that angle ADC.
And then another way that we can say angle BOC, wait, not BOC.
You know that ADC is
Yeah.
AOC plus BOC.
Angle ADC is equal
Or
to
ADB. Sorry.
angle,
Angle
oh.
ADB is equal
no, ADC is equal to ADB,
to. Oh yeah.
ADB plus angle BDC, which is
Switch
equal
that
to,
around. Which
Uh,
implies. Oh.
where was I? Angle ADC is equal to,
Half
oh,
of AOC.
then let's do our substitutions.
Yeah.
What's angle ADB equal to?
That's the one
Oh.
I'm looking for. So you gotta get that one.
Yeah, so let's do 1/2 angle AOC. And then I'm going to substitute in on both sides, right?
1/2 angle AOC equals.
Would it be plus?
Yeah, that's fine.
So then angle ADB,
It's AOB.
oh, wrong one. Angle BDC is equal to
1/2 BOC.
1/2 BOC. Oh, let me rewrite this. Is equal to 1/2 angle
It's not equal to.
AOB plus angle BOC.
Oh.
So maybe just distribute the 1/2s. There we go. 1/2 that plus 1/2 that, right?
Right.
So get rid of this middle.
Where
Let me
is
just
that?
skip.
That's what we're trying to prove. 1/2 AOB.
Okay, I shouldn't have done that. 1/2 angle AOC, right? Which is equal to 1/2, and what's angle AOC? That's angle AOB plus angle BOC,
Oh, I see.
That's what I thought you were
which is
doing.
equal to 1/2 angle AOB plus 1/2
BOC.
angle BOC. Now I already know that angle, here's my picture. I already know that angle BDC is 1/2. 1/2 which one? BOC. So I know that these two are equal, right? Angle BDC is equal to 1/2 BOC.
So you can cancel out.
So cancel out from both sides, and that leaves me this. Angle
ADB is half of
ADB is equal to 1/2 angle AOB, which shows the other case. Okay.
Right.
Hopefully they can see that on camera. That is a pretty bad marker.
Sure, it's fine.
But that was the last cool theorem in that chapter. So that finishes off
12.
chapter 12.
Can you do it with the not inscribed angle?
The theorem isn't true for a not inscribed angle.
So it's only an inscribed angle.
It's only for an inscribed angle. So I think that those diagrams there were just telling you what an inscribed angle was, so you knew what it was talking about. But yeah, so that finishes chapter 12. So we have logic and sets, then higher dimensional space, then analytical geometry,
Did you say
then
log?
philosophy of math.
What's that word?
Oh, not logic, loci.
Set of points suspects that.
So yeah, you usually talk about a locus for a set of points that meet some sort of criterion.
Like even numbers.
It's typically related to a graph. So for example, a circle is the loci of points distance r from O
Okay.
is a particular circle.
Hmm.
It's very much tied to
Points is a set of all.
when we're thinking about a graph of something, then we typically call it the loci of points. Very much when we're talking about lines, for example. So if I say y equals 1/2 x plus 2, that's a
It's
loci
set
of points
that fulfill that condition.
with this, that meet that condition. Yeah. So that's typically when we use that word. The loci or the locus of points. So, yep, we'll go over that in sets. Then we'll do a little bit three-dimensional geometry, then analytical geometry, and then philosophy of mathematics, which we've already talked about some, so we can go over it again. So we probably have 2 more classes and we're done with the book.
I'll be there.
You'll be there for both of them?
I said I better be there.
I need to start gathering up people's textbooks that are done with this class.